Having seen several examples of forcing functions that are periodic, but not necessarily a sine or cosine, we now explore what the simulation results would show us about how a spring and mass system responds to those forces. Our first example is where we force the system with a square wave. We have an on force, and then it turns off. We have an upwards force, then it turns off. Then an upwards force, then it turns off. When we went through the full Laplace transform analysis of the effect of this square wave on a spring mass system, we saw that we had different intervals with different solutions, but there was a pattern to those solutions. In the first interval, we end up with a sine with amplitude 1, but a little offset, then an amplitude 2, then an amplitude 3 offset, and then amplitude 4. And what we could see is, as time goes on, we're going to have oscillations with larger and larger amplitudes. Let's see that as a simulation. Here we see the spring mass system, and we'll be able to track the force being applied. We'll watch it through once. So we see the force turning on, and then off, and then on, and then off. And notice it's in perfect synchrony with the natural oscillations. We turn the force on just when the mass would hit the bottom. That's not necessarily what would happen in every case. It just happens because we chose the on-off times to match the natural oscillation periods. Let's watch that again. I'll point out a couple of other features as we go along. We're pausing to see what's going to happen initially. Then we see the upswing. And then you can see how these oscillations might work. There's a tall oscillation because things are centered a little bit higher when we're pulling up. When the on force goes on, we actually overshoot the zero line. We actually have an equilibrium that's a little bit higher. And the net effect of that is to produce larger and larger oscillations. We see that with this 1 minus offset in the solution and 1 minus offset. Looking at the solution, if you imagine this region here, what we'd see is this is an oscillation, is a sine wave that comes up, has an equilibrium here, and then we just reach the tip of it, and then we turn off the force. So then we just get a perfectly natural unforced oscillation. You see it's symmetric from here to here. When you look at this next valley to peak interval, it's stretched out a bit. The center has been moved over to this point here between time 4 and time 6. We see that in the mathematics as between 4 and 6, there's a 1 vertical shift to the y values. And then we have an amplitude that's larger so that these things all join together seamlessly. And then we see that pattern repeated. It's a perfectly natural oscillation here centered at 0. And then the next oscillation is centered a little bit higher, and it goes up higher as a result. And then it just relaxes back down. Let's play that one more time before we move to a different forcing function. Force is on, and then it relaxes. Force is on, and then it relaxes, on, and so forth. And that shows how very quickly we could end up in trouble with the physical system. If this mass went one more cycle, it would run straight into its support. The second forcing function we experimented with was the sawtooth, where we had the force at -2, so pulling downwards, then gradually lightening up, then pulling upwards, then instantly turning around and pulling downwards again. We'll see a slightly more interesting initial response to this curve, as indicated by the slightly more complicated function that we found on each interval here. But we still have the same pattern of increasing sine amplitudes as time goes on. The other ingredient, simplified from what we did in the notes, is that it might look like there's increasingly large subtractions here, but keep in mind at the start of the interval, this value would be at t equals 0, so this would equal -2. At the start of this interval, t starts at 4, so this would start at -2, and this would start at 8 minus 10, -2, and -2, and so on. So this is consistent from interval to interval, even though it might not look like it at first glance. Here we have the same spring system, and we're going to initially be pulling down. So we froze frame here, then we pull down, then pull up, and then quickly pull down. And notice there's a little bit of a hiccup there at the beginning, but now, after a few cycles, we see that the natural oscillations and the oscillations from the forced function are totally in sync. And in fact, if we were to let this go on any further, we would have things blowing up on us, or breaking or crashing. Notice what we see over here though is that nice linear growth in the form of the solution. This function, because it's a more complicated forcing function, we've plotted here at the top, so I'll trace that out. Keep your eye on these two graphs for the next iteration. Here it is at the start again, and it's off. So notice the force, and notice the response in the curve. When we have a sharply increased negative force, we pull down really hard, and we can see there's a bit of an acceleration in the downwards motion of this mass. And again, because of that equal frequency between the natural oscillations and this forcing function, we get this progressively larger and larger amplitude. Let's see that one more time. Larger, pulling up when it's going up and pulling down when it's going down. And notice we've got the synchronicity where when we reach a zero force, that's exactly when it's at its center point here. You can see the 0 point matches when we're transitioning from moving up to moving down. So that demonstrates again that we can have resonance even though the forcing function isn't necessarily a sine or a cosine. It's not a mathematical property of those trig functions specifically, but just that the period of the forcing function is equal to the period of this natural oscillation. As one last demonstration, what we're going to do now is use our sawtooth function, but use it with a frequency that's not a match to the natural frequency of the spring mass system. The natural period of the oscillations for the mass spring was 4 seconds per cycle. We're going to use a period of 2.5, something away from 4, for the sawtooth function now, and see what that gives us. So we'll start off with a downwards force, and then pull up. Downwards force and pull up. Downwards force and pull up. And here you can see the conflict between the natural motion where the spring system wants to go and the fact that we're pushing on it with this external force on roughly the same magnitude. And we do not get crazy buildup of energy in this system here. We get quite the opposite, in fact. We get sort of randomish, harshly pushed and pulled response to the system. Let's see that again. Keep an eye on the right-hand side this time of the association between the natural oscillations and this forcing function. Here it goes again. So the pattern of the oscillations, or the forcing function, is exactly the same as before. It goes big and negative, push down, then 0, then pull up. But the response is just completely different because they're not at the same frequency or don't have the same period. You never get the alignment that we had before between when the forcing function is pulling down and up and the natural movement of the mass when it's moving down and up. And as a result, we do not see resonance. So again, resonance isn't a particular feature that is triggered by the shape of these functions, but it's by the period of them. How long is this cycle, and how long is one natural unforced oscillation on the spring mass?